Thank you, everyone, and thank you, Dr. Kim and Dr. Chung, for hosting this event. I'm really excited to be here with all of you. Now, how many of you were at the reception dinner last night? I was there. Was anybody else at the reception dinner last night? There was a fantastic band who were playing traditional Korean music and modern Korean music, and they were singing songs about love, and the theme of this event is quantum love, right? And the E in quantum love is engagement. So we're going to try what that band was doing last night. We're going to try a little engagement. I would like everyone in the room to just lift your hand. Raise your hand for me. Everyone, there's no qualifying criteria. You just raise your hand and we've got our hands up. Okay, now put your hands back down. How many of you now are quantum physicists? All right, we got Charles in the front and a couple in the back. Okay, great. Honey, yeah, good to see you. All right, how many of you are in the Department of Computer Science? Quite a few. Okay, how many from mathematics? We've got some mathematicians here. And statistics? Anyone from statistics? And anyone working on machine learning, artificial intelligence techniques? We've got a few of those as well. And then in terms of the life sciences and pharmaceutical sciences? Up front, all right, great. Okay, so everyone who did not put up their hands for quantum physicist, this presentation is for you. Okay, and I'd like to see a little quantum love. Everyone put up a heart here. Let's see your quantum love. I learned this heart technique last night. All right, so quantum technology evangelism is my role. I help global businesses and organizations to understand quantum computing and the transformational impact that it can have for them today. I'm really excited to be with you here. I'm not going to spend a lot of time talking about this slide, but it gives you a bit of an idea about D-Wave. We were the first to commercialize quantum computing systems, and we're also the first quantum computing company that has customers who are running applications that are quantum hybridized as part of their production operations. All right, so I'm going to begin at the beginning. What is a quantum computer? Right? It's a device that uses quantum effects to perform calculations that are too slow or too hard for classical computing systems. Okay, so that means that quantum effects must be a resource for the computer. What kind of a resource does that actually represent? Well, it turns out that we've determined multiple ways to use quantum effects as a resource in a computer, and those are the different models of quantum computing. D-Wave is the only company that is building two primary models of quantum computing, and I'm going to be talking to you a lot about annealing because that is the area we began with. So let's look at annealing. There, quantum effects is a resource that allows the computer to move between solutions more quickly. So let's say you're a business and you're doing at-home grocery delivery driving and you want to assign schedules to your workforce. Well, you might have a current schedule that you're working with, and what you'd like to do is transition to a better schedule. So you want to make that state change faster. That's the idea behind using quantum effects and annealing. Now let's contrast that with gate model. In gate model, we're using the quantum effects to allow the computer to store more information. It turns out that the choice that we make about how we want to use quantum effects as a resource for computing determines what skills we need to program the systems, how quick it is to develop the systems and build the hardware, and also the applications that they're going to be useful for. Because what we now know from the research community is that if we want to tackle problems in quantum optimization, we must have annealing quantum computers. The reason for that is because the overhead for using a gate model system is too high. But we also know that there are very important applications in quantum chemistry and in 3D fluid dynamics, fluid flow calculations, that we can only do with gate model systems. So in the future, we're actually going to need both of these quantum computing models in order to be able to provide the full suite of calculations that quantum computers can do faster than classical computers can. Okay. Now, I'm going to be talking for most of the rest of the presentation about D-Wave's mature commercial quantum annealing quantum processors. These are some of the most studied quantum computers on the planet. There have been nearly 10,000 research papers published on D-Wave quantum computers, and more than 150 of those have been published in Science and Nature portfolio publications. In fact, we've crossed over the point of having 1,300 publications per year. But what's significant about that, and like the survey I did at the beginning of this, we're engaging young, talented researchers in the areas of computer science, mathematics and statistics, because you don't need to know quantum physics to program quantum annealing systems and put them to use in applications. So in fact, it's a very complementary technology to the center here that's doing work with the IBM quantum computing system. Now, I've been asked from time to time, what is the most significant development in quantum computing in the last year? And this is my answer. This is information processing beyond classical computing that is incredibly energy efficient. We published a preprint where we were able to demonstrate a calculation that we could do on our quantum computers in 20 minutes that would take a high-performance computer more than 1,000,000 years. Now, some of the members of my quantum computing community use the term high-performance computer a little loosely, but I'm using it in the formal sense here. We used 100,000 hours on the Frontier and Summit supercomputers at Oak Ridge. The Frontier supercomputer is the largest supercomputer on the planet right now, in order to do these calculations. And we were able to do these calculations here on the systems at small scale. We chose a problem that has been well studied so that we knew exactly how the difficulty would scale with the system size. And then we were able to project how much effort would have been required to match the results we were getting with the quantum processor. And this threshold here is 1,000,000 years on that Frontier supercomputer. Now here's the key point. D-Wave has produced 5 generations of commercial quantum annealing processors. Every single one of those generations of commercial quantum processors consumes 15 kilowatts of power. That's about as much power as we're using in this room right now. For a high-performance computing system, that's incredibly low power. So while all of the CPUs and GPUs that we're using have been steadily growing in their energy consumption, why is it that these commercial quantum processors are not growing in their energy consumption? It's because the quantum annealing processors that are made out of superconducting metals at their core consume 1,000,000 times less power than a mobile phone. So what this indicates is that if we can take workloads that are very difficult for high-performance computing systems in the areas of material research, in the areas of optimization, industrial optimization, and in the areas of artificial intelligence methods, if we can take those very difficult calculations for classical computers and move them onto these quantum computers, we can dramatically reduce the energy consumption for those calculations, which is a pivotal issue in the world today. Now, the kind of work that you're doing here at Yonsei is absolutely critical. And there are a community of other high-performance computing and computing universities who are similarly doing what you're doing. So at the Forschungszentrum Jülich, the Jülich Supercomputing Center, they've purchased one of our annealing quantum computers, which they expect to connect to their Jupiter supercomputer, Europe's first exascale HPC. And this is a photo of the D-Wave quantum computer currently at their site in Germany. Their focus is going to be on using these quantum computing systems for modeling and emulation, and also for provisioning quantum computing systems, much as you're doing here in the Korean region, to study the integration of high-performance computing systems and quantum computers in terms of how they work effectively together, and to create quantum computing user infrastructure for science and industry. Now, they have a model which includes having on-site both annealing quantum computers and gate quantum computers, because they also recognize that there are different uses for those two technologies. And so as they want to engage their full community, they can do that by supplying those users with a variety of quantum computing systems that are complementary to one another. Now, this is a pivotal moment in the quantum computing industry, and D-Wave is focusing on shifting the conversation away from experimentation. Yes, there is some very valuable experimentation that still can be done. We need the research community to explore and answer open questions that those of us in the industry of building quantum computers don't have the resources to tackle. But we also can now start talking about conversations about the operational use of quantum computers by businesses. In order to do that, we don't have to talk about toy problems. We can talk about problems at enterprise scale. They're full application problems. And we don't have to just talk about the potential impact in the future. There is tremendous impact in the future for quantum computers. We can talk about our return on investment that those businesses can measure today in their operations. So let's talk about some of those use cases. The first is Pattison Food Group. Pattison Food Group owns 13 different grocery brands in Western Canada. During the pandemic, we began working with them because at-home grocery delivery became incredibly important to their business because a lot of their customers couldn't necessarily come into stores to do their shopping. And we worked with them to help develop an application to produce the schedules for those at-home grocery delivery drivers. And when we did, we were able to reduce the scheduling time by 80%. That application has been in production since October 2022. So right now, there is a full-time application running at Pattison Food Group for these delivery drivers, and it's just been running continuously since 2022. Since then, they expanded to a second application in their stores to tackle a difficult problem. They have machine learning methods that give them a forecast of how many customers are going to be coming in each day of the week and each week of the year. And then they have to schedule their employees in store in the different departments based on their seniority, and they have to optimize a full work week for their employees. That is now an application that they have built, they've tested, they're taking it through their first phase of release, and they're already at the stage where they're expecting to save their workforce 50,000 hours every year. So the great thing about these applications we can use these quantum computers for is that applied in businesses at scale, they have a tremendous impact. And when we talk about return on investment for quantum applications, we have to consider everything in terms of their operations, their workflow, the impact on their people and processes, and that has been achieved here. What's really significant about that second application is that the team members who were responsible for scheduling, they were the most senior employees at the company. And they had to spend dozens of hours behind their computers each week working on these schedules. Well, now they don't have to. They're able to actually get out and work with their more junior employees and train them on the important elements of their business and work directly with their customers. So a really significant impact on their employees and their business in terms of their business processes. Now, you may have heard about this example. NTT Docomo in Japan has used our quantum computing systems to optimize their mobile telecommunications networks, specifically the paging signals that pass between the base stations and us as cell phone users. They've been able to reduce the number of paging signals that are needed in the network during peak loads by 15%. And they are currently scaling this application out for full production use in Japan nationwide across 250,000 base stations. So a very significant network that this is being used in. And it effectively increases the capacity of that network by 15%. Now let me talk to you about this third example. Ford Otosan in Turkey is looking at their Ford transit line and the production of the vehicles on that line as the conditions change. They want to be able to schedule which equipment is used for manufacturing their parts and their vehicles so that the whole production line is as productive as possible. And we were able to work with them to allow them to schedule 1,000 vehicles in 5 minutes, an 83% savings from their previous 30-minute time, and it also reduces the number of business constraints that were violated in those solutions. Now, this application is yet to move on to full production, but it has been tested in their production line, and they know that they can get a high return on investment with this application. Okay, so let's talk about, those are some of the examples of applications that are currently being used, are currently running and have been running for years, and are on their way towards moving in production. There's so many exciting applications. We've got literally 100 organizations around the world who trust D-Wave to use our quantum computing systems and bring them value because we have the performance, the reliability, and the use cases to allow them to apply this to their business and see value now. And that's why we're all looking to quantum computing, not just for exploring the science behind the systems, but actually to bring productivity, efficiency, and efficient energy use to our economy and our nations. In order to support these applications, D-Wave has produced 5 generations of commercial quantum processors. Those are the advantage quantum computers. We've also have a cloud service called L.O.V.E. And this is the system that has the high reliability. Its availability is 99.9% of the time. We could get online right now, submit problems. When we're submitting problems to the QPUs, we can get sub-second response times immediately as we're programming them. In that system, we've also got these ocean open source tools. And the open source is really valuable both for businesses, because it allows them to inspect the application code and make sure that it's secure, but also for this community, this broad community from different fields. because the quantum physicists will start programming the systems at the low machine instruction layer. But the mathematicians and computer scientists may be coming in at the middle layer. And then the software developers and application developers in industry will coming in at the top layer. And as each of those communities contributes to that open source library, we get a compounding benefit for the businesses that are building applications on top of it. And at D-Wave, we also have a program for helping folks wherever they are on their journey from discovering which applications are suitable for quantum computing, because it's important to note, although we could submit any kind of problem that a classical computer could do to these quantum computers, they can't accelerate all problems. We just want to focus on the problems that they can accelerate. And once we've identified those, then we want to start rapidly building proof of concepts and then moving them to production. We have a worldwide network of quantum computers online right now. We have systems that are in Burnaby, Canada, also at the University of Southern California in Los Angeles. I talked to you earlier on about the system at ULIC, Germany, and there's a new system going in Huntsville, Alabama, a little bit later this year. Now, one of the important areas of research, it's actually been pivotal and critical for the use of quantum computing systems, has been the hybridization of classical and quantum computers. When I first started coming out and meeting with users, I was teaching them about the machine instructions for our quantum computers and to help them hybridize the systems. We even created an entire open source library to show users how to hybridize classical and quantum computers productively. But the response from our customers was, hey, that's great, and I love that it's open source, but we don't want to have to become experts in those algorithms. We want to solve our business problems. So we've actually developed online hybrid solvers here that are allowing people to tackle enterprise-scale problems much more quickly. It makes the program development much faster. It has high availability. And as we produce new quantum processors, and they have dramatic performance scaling relative to the previous generations, all of the customers running on these hybrid methods get the benefit of that evolution. Because the hybrid solvers take in their large problems, they begin working on them with classical computers, and those classical computers break pieces out and call the quantum computers on the customer's behalf in order to help it move through the solution space and find high-quality solutions quickly. Okay, I'll finish on this slide with a minute and a half left. We have our user group meeting at Qubits 2025. We're talking about realized quantum applications, March 31st and April 1st in Scottsdale, so hopefully some of you will be able to attend. Check it out online, and yeah, maybe we'll have time for a couple questions.
Do you have any questions? I want to ask a question.
Please.
So some years ago, there were some comparisons going on between the coherence Ising machine and quantum annealing machines. So do you have some saying on this?
Well, after some of that initial work, the results began to fade away. So I saw less and less development from the coherent Ising machines. I'm not sure if they continued that project. For the folks that I know in like optimization algorithm development, the coherent Ising machine looked like a mean field solver. And that's a very valuable solver if it can be accelerated, but it's also something that classical computers can already do very effectively. Whereas in the benchmarking tests against our quantum computers, we've actually found that they're able to solve problems that classical computers find very difficult.
And also D-Wave is from the high temperature superconductivity, right? And do you use this high temperature superconductor?
No, a little bit of trivia here. So the founders of D-Wave were members of the high temperature superconducting community. They actually designed their first qubit using high temperature superconductors, which use D-Wave superconducting wave functions. But that design didn't turn out to be the one used in the production, but we kept the name. So we're still using low temperature systems, which is S-wave superconductivity.
So historically.
Yeah, historically, yeah, that's right.
And another thing is, I'm not familiar with your system, so is there some kind of metric like a quantum volume to evaluate the performance of your system?
Well, the difficulty with quantum volume, which is really just the number of qubits multiplied by the connectivity and its coherence, is that there isn't really a close connection between that and then the results we see in applications. So that's why I put the focus today on the benefits that people have seen once that technology has been put right into their application workflow. However, we do have a whole series of benchmarking publications, both individually proving quantum mechanics is accelerating it, and against classical computing systems. So if you've got questions, if you'd like those references, come and talk to me afterwards and I can send them to you.
Okay, thank you. Any other questions? Okay, let's thank our speaker again.
Thank you very much.